If you're a student in pre-cal and calculus, then you have to evaluate trig functions without a calculator, and you know that memorizing the unit circle is hard. So today I'm going to teach you a trick to evaluate trig expressions with just your hand and your brain, so you don't have to memorize the unit circle. Once you get the hang of it, it's very intuitive, especially for the inverse trig functions. By the end of this video, you'll be able to evaluate trig functions without memorizing the unit circle. First, let's start with some background information to make sure you know everything you should know coming into this. So we start with the unit circle. The unit circle has a radius of 1 and it's centered at the origin. The circle has 360 degrees, which is also equivalent to 2 pi radians. Since these two values measure the same angle, we can stack them on top of each other, and that expression equals 1. And this is useful because we can multiply anything by 1 and we don't change its value. So we use this division of two equal measurements in different units to convert between units. And you want to arrange it so that the unit that you have cancels away and you introduce the unit that you need. This fraction will also simplify to 180 degrees over 2 pi. 180 degrees over pi. So for example, if we wanted to convert 30 degrees to radians, we want to cancel the degrees, so we're going to use the one with degrees at the bottom, and we want to introduce radians, so we would put radians in the numerator. And so now our unit is in radians. That would be 30 over 180 would be pi over 6. And similarly, let's say we had 5 pi over 4 radians, and you wanted to convert that to degrees. Well, you've got radians in the numerator. You want to use the conversion factor with radians in the denominator. And you want to introduce degrees, so use the one with degrees in the numerator. And so then be 5 times 180 divided by 4, 225 degrees. Another way to think about radians, if radians is a weird unit to you, is that 1 pi radian is a half of a circle. So however many pi's there are is however many half circles there are. All right, so now back to the unit circle. We can draw a radius at any angle on this circle. And in math, we're going to use the angle with respect to the horizontal axis. In physics, sometimes you'll use the other way, but we'll talk about that. And one of the special things about this, because we have our XY plane, we can actually create a right triangle with an X and a Y from any radius that we have. And that'll always form a right triangle because these are just the X and the Y axes. And the special thing about right triangles is that we have this relationship between the sides and the angles, commonly taught as SOH CAH TOA. Right? And so on this triangle here, the top side is going to be our radius. And that's also going to be the hypotenuse. The X is the side that's touching the angle, so that one will be adjacent. and the y is the one that is the opposite side of the angle. So the y would be our opposite, right? And so with the SOH CAH TOA relationships, it's the sine of the angle equals the opposite over the hypotenuse. Cosine is adjacent over hypotenuse. And then tangent is opposite over adjacent. And tangent also, by the way, is equal to sine over cosine. So conceptually, sine and cosine, they calculate the proportion of a 2D line's distance going in either the x or the y direction alone. So when the angle's with respect to the horizontal, like we've shown it, then sine tells you the proportion of the 2D line that's going only in the y direction, and cosine would tell you the proportion of the line going only in the x direction. The hypotenuse represents the true line, which is going in the angle of theta. Another interesting thing to note is that tangent, opposite over adjacent, when we have it like this, is y over x, right? And so tangent is also equal to the slope. If you plug in an angle into tangent, the output will be the slope of the line at that angle. I mentioned, the with respect to the horizontal axis, meaning our angle is formed with this one. Sometimes in a physics course, you might get your angle with respect to the vertical axis like that. And so it's best not to memorize that sine is with y and cosine is with x. In math classes, that will be how it'll always be. But if you're in a physics class, just remember you can always draw a picture and start with the SOH CAH TOA relationships. All right. So also we have inverse and reciprocal trig expressions. So we have the reciprocal of sine is equal to cosecant. The reciprocal of cosine is equal to secant. And the reciprocal of tangent is equal to cotangent. And one thing that might help you remember which one goes with which is if it has a co in the reciprocal, then the other one does not, and the other way around, right? So like sine, cosecant, cosine, secant, tangent, cotangent. Just to note, we're not even going to worry about evaluating reciprocal trig expressions. Anytime we see them, we're just going to convert them into the regular trig expressions and then do some algebra on that. So now let's talk about the inverse trig functions. The inverse trig functions, they're sometimes called arc functions. Different teachers, different textbooks, and whatever, they might use those interchangeably. Right, so it'd be called like inverse sine. That would just be the same thing as arc sine, and so on with the inverse cosine and inverse tangent. There's arc cosine and arc tangent. The whole reason for needing the inverse trig functions is when you want to solve for the angle. So we can just derive the inverse ones from the original trig functions, right? So if sine is equal to opposite over hypotenuse, then we can apply the inverse sine function on both sides of the equation and get that the angle is equal to the inverse sine of opposite over hypotenuse. Similarly with cosine is adjacent over hypotenuse. We can apply the inverse cosine to both sides, and we get the angle is the inverse cosine of adjacent over hypotenuse. And then similarly from tangent being opposite over adjacent. Apply the inverse tangent on both sides, and the angle will be the inverse tangent of opposite over adjacent. So these are actually three different solutions. They should give you the same angle if you know all the sides of the triangle. All right, so we talked about the function of the regular trig expressions. They give you the proportion of the line that's in only the x direction, or the proportion of the line that's only in the y direction when you input the angle. So the regular trig functions, they can convert an angle into a distance in some direction, or if it's tangent, it'll convert the angle into a slope. The inverse do the opposite of that. So given a distance or a proportion of distances, we can calculate the angle that that line must be at in order for it to form a right triangle. There's also another important concept we should touch on with solving for an angle, because technically there's infinite solutions for any angle. So let's say this is our angle. I don't know, that looks like 45 degrees. Well, we can do any full circle rotation and end up at the same angle. And actually that could happen, another time. We could do 3 full circles. We could really do infinite full circles and actually have the same angle. And so basically, if we use one of these trig expressions and we solve for one angle, let's say if it was 45 degrees, for example, we could actually also have, plus any integer multiple, actually plus or minus, right? Because we could rotate left or right. Plus or minus any integer multiple of a full circle's rotation. Okay. And just in case we were using radians, let's say this would be pi over 4 for 45 degrees. It would also be plus or minus n times 2 pi would be the full circle in this case. Though there are infinite solutions for an inverse trig function, the calculator is going to only output one. And so if you only had to pick one, which one do we pick? So if this is our xy axis, then the positive x-axis would be 0 degrees or 2 pi radians. The positive y-axis would be pi over 2 or 90 degrees. The negative x-axis would be 180 degrees or pi radians. The negative y-axis is 270 degrees or 3/2 pi. That's 1 1/2 pi. Oh wait, I did say 2 pi. This is correct, but really 0 degrees would be 0 radians. But it is also 2 pi, as we mentioned, any full circle, right? So this one is also 360 degrees. So the output range for inverse sine is going to be from negative 90 to 90 degrees. Or that could also be written as negative pi over 2 or pi over 2. Right? And so sine inverse is only ever going to give you an angle in quadrant 4 or quadrant 1. And if it's in quadrant 4, it's going to be the negative angle. That just means how far down did it rotate if it's negative. And so another important thing to note about this, since we're associating sine with the y value here, this represents the full span of angles for all the y values from fully negative to fully positive. So then likewise, since cosine is associated with x, the output of inverse cosine is going to give you the full span of angles from negative x to positive x. So cosine inverse is going to have an output range from 0 degrees to 180 degrees. Or 0 radians to pi radians. I guess technically I should have been using brackets this whole time. It can give you those values at the end. All right. And so then what about tangent? Oh, wait, hold on before we move on. So cosine inverse has an output range in quadrants 1 and quadrants 2. Okay, now what about tangent? Tangent, remember we said is sine over cosine, so it's kind of associated with both. Which quadrant are we going to put the outputs in? Just by convention, inverse tangent has the same output range as inverse sine. And so that's going to be from negative 90 degrees to 90 degrees, or negative pi over 2 to pi over 2. And likewise with sine inverse, inverse tangent's only going to be in quadrant 4 or quadrant 1. And if it's in quadrant 4, it's going to have the negative angle. The last other thing that we should review is actually pretty simple, but it's just the sines of x and y and the slope of a line that are in each quadrant. Right, so in quadrant 1, x is positive, y is positive. In quadrant 2, x is negative, y is positive. In quadrant 3, both are negative. And in quadrant 4, now x is positive, but y is negative. Okay? Now a slope in quadrant 1 is going to be positive. A slope of a line going through quadrant 2 is going to be negative. Slope of a line in quadrant 3 is positive. And the slope of a line in quadrant 4 is negative. So notice that the ones that are diagonal from each other have the same slope. And that's actually because any given line, the two opposite ends of it are separated by 180. And so how does this tie into everything? When x is positive, cosine is going to output a positive value. when x is negative, right, then the other way, cosine output is negative. Same with y. If y is positive, cosine output, if y is positive, sine output is positive. If y is negative, sine output is negative. And if the slope is positive, then the tangent output is positive. If the slope is negative, then the tangent output is negative, right? Because slope is tangent. So then what does that mean here? Well, when x is positive and y is positive, that means, let's say, cosine and sine are going to be positive. And when the slope is positive, that means that tangent is positive. So in quadrant 1, all of them are going to have a positive output. In quadrant 2, x is negative, so cosine is negative. Y is positive, so sine will give you a positive value. The slope is negative, so tangent will give you a negative value. And quadrant 3, both of them are negative, so then cosine and sine will both be negative. The slope is positive, so tangent will be positive. Lastly, in quadrant 4, x is positive, so cosine will be positive. Y is negative, so sine will be negative. The slope is negative, so tangent will be negative. Just to tie all that together. Okay, now let's learn the hand trick. Hold out your left hand with every finger straight. We're going to use the thumb and the pinky to represent the x and the y axes. And then each of our fingers is going to form one of the important angles that we would ordinarily have to memorize from the unit circle, right? So the x-axis, remember, is 0 degrees, also 0 radians. The y-axis would be 90 degrees, also pi over 2 radians. These ones in the middle, right, is going to be our 30 degrees, 45 degrees, and 60 degrees, or pi over 6, pi over 4, and pi over 3. So to use this hand trick, all you need to do is fold down the finger for the angle you're trying to evaluate, and then use one of these formulas. So the sine of the angle is going to be the square root of the fingers below divided by 2. Cosine of the angle is going to be the square root of fingers above divided by 2. Tangent, right, which is equal to sine over cosine, is going to be the square root of fingers below divided by fingers above. And just to note, in the sine and the cosine formulas, the fingers is in the square root. The 2 is not a squared. You could move it in there and say under the square root have divided by 4. With the tangent, it's both the square roots of fingers below and above. Okay, so let's do an example. We're going to evaluate each trig expression at pi over 3. All right, and just by the way, pi over 3, that would be equivalent to 60 degrees. That one is going to correspond to the index finger on our hand trick. So you would fold down your index finger. Now for sine, it's the square root of the fingers below divided by 2. Cosine, square root of fingers above divided by 2. And square root of 1 is just 1. So that's 1/2. Tangent, that's going to be the square root of fingers below divided by above, square root of 3 over 1, right? That's just square root of 3. Now, to evaluate the reciprocal trig expressions, remember, we're not actually going to directly evaluate those. We're just going to do it in relationship to the regular trig expressions. So cosecant of 60 degrees, that would be 1 over sine of 60 degrees. And we solved that as square root of 3 over 2. So 1 over means we're going to take the reciprocal of it. It'd be 2 over square root of 3. All right. There's nothing wrong with this number directly, right? But back, in the 1800s, it was a lot easier to multiply by square roots than to divide by them. And so we have this rule in math that we're not allowed to have a square root in the denominator. And so what we can do is we can multiply this by 1 in a way that we're going to convert the denominator not into a square root anymore. And so then that would be 2 square root of 3 over, and square root of 3 times square root of 3 would be 3. Okay, for secant, that's just going to be 1 over cosine, which we calculated that as 1/2. So 1 over that would be 2 over 1. That's just 2. All right, and then tangent will be, not tangent. Cotangent will be 1 over tangent. We said tangent was square root of 3, so it would be 1 over square root of 3. We'll do the same trick we did for cosecant. We're going to multiply this times square root of 3 over square root of 3. And we get square root of 3 over 3. Okay. Example 2. Evaluate each trig expression at 0 degrees. 0 degrees is also equivalent to 0 radians. 0 degrees on our hand trick is the pinky. So fold down your pinky. Sine would be the square root of fingers below over 2. You have 0 fingers below, so that's just 0. Cosine, square root of fingers above over 2, so that's square root of 4 over 2. That's 2 over 2. That's just equal to 1. Tangent of 0 is sine over cosine, so that's 0 over 1. It's just 0. We can also do square root of fingers below over above. Either way, we have 0 in our numerator. So tangent is 0. For cosecant of 0, that's 1 over sine, right? So that's 1 over 0. That would be undefined. It's going to approach infinity. Secant of 0 would be 1 over cosine. That's 1 over 1. Just 1. Cotangent of 0, 1 over tangent of 0. So again, 1 divided by 0. It's the same thing as multiplying by infinity. Undefined. All right. Example 3. Evaluate each trig expression at pi over 4. We're going to use radians this time. Pi over 4 would be your middle finger. So you're going to fold down your middle finger. Sine is going to be the square root of fingers below over 2. Cosine is the square root of fingers above over 2. Tangent is sine over cosine. They're equal, so it's just going to be 1. Also, square root of fingers below over above. It just comes out to 1, right? And also that makes sense because pi over 4, 45 degrees, is perfectly in the middle of x and y, going diagonally straight through them. And so it makes sense that the proportion of the line in the y direction, sine, the proportion of the y in the x direction, cosine, are equal to each other because it's right in the middle. And the slope of that line is 1. So that's why tangent gives us 1. Now for cosecant, it's just 1 over sine. So we would have 2 over square root of 2. We're going to do the same trick to rationalize the denominator. We multiply by 1 so that our denominator becomes a rational number, and we move the square root up to the top. Okay, and actually then, yeah, now we're going to cancel out that 2. So we just have square root of 2. For secant, pi over 4, it's going to be actually equivalent to cosecant for this angle. It's 1 over cosine. So again, 2 over square root of 2, right? We just determined that that was square root of 2. And for cotangent, it's 1 over tangent. So 1 over 1 is just 1. Okay. Now that we got the hang of it, what if the angle is not between 0 and 90 degrees? So when this happens, we can use what's called a reference angle, which is between 0 and 90 degrees, commonly used alpha, so that we can still find the same sine and cosine value. But then in order to make sure that we get the positive or the negative sign correct, we have to bring in our understanding of which sign is positive in which quadrant, right? So like we discussed earlier, in quadrant 1, both x and y are positive, so cosine, sine are positive, and the slope of a line in quadrant 1 is positive. So all cosine, sine, and tangent will be positive in quadrant 1. In quadrant 2, remember, x is now negative. The slope of the line is negative. So cosine and tangent will be negative, but then y is positive in quadrant 2. So sine will be positive. In quadrant 3, now we have both x and y are negative. So sine and cosine are going to be negative. right? But the slope of the line in quadrant 3 is positive. And then in quadrant 4, x is positive, so cosine is going to be positive. But now y is negative and the slope of the line is negative, so sine and tangent will be negative. So we just have to bring that understanding in, and we still use the hand trick now instead using alpha, which will be our reference angle. That brings us to example 4. Evaluate each trig expression at 225 degrees. All right, so first of all, we need to figure out which quadrant does our angle stop in, right? And how do we figure that out? Well, okay, we got 0, 90, 180, 270. Just see where does it lie, right? So it looks like in this case, we're going down this way. So that would be our angle of 225 degrees. All right, so that means we're in quadrant 3. What did we say about quadrant 3? We said x is negative, so cosine is negative. We said y is negative, so sine is negative. The line has a positive slope, so tangent is positive. Okay, now our reference angle is always going to be measured with respect to the horizontal. Just where can you find an angle that's with respect to the x-axis that's between 0 and 90? It's going to be right here. So this is going to be our alpha. Now, how do you determine what alpha is? It's just an angular span. So you just subtract the bigger angle minus the smaller angle. So in this case, alpha would be 225 minus 180, which is 45 degrees. So that means that we can use the hand trick to evaluate 225 degrees using 45 degrees on our hand. And then if we're doing cosine and sine, we're just going to add a negative. And if it's tangent, we're going to keep it positive. So sine of 225, right, that would also, you could also write that as the negative sine of 45 degrees. You would fold down your middle finger, and that's the square root of fingers below over 2. And remember, it's negative. Cosine of 225 degrees. Again, fold down your middle finger, square root of fingers above over 2, and it's negative. Tangent, well, since sine and cosine give you the same number, tangent will be 1, and it stays positive. All right, so then for cosecant, remember, we never worry about using these directly. We just convert it into sine and then do sine. So we already got our sine figured out, negative square root of 2 over 2. Flip that, negative 2 over square root of 2. And remember that just turns into negative square root of 2. Secant of 225 degrees, that'll be 1 over cosine. It's equivalent to cosecant for this angle. Negative 2 over square root of 2, that will just simplify to negative square root of 2. And then cotangent of 225 degrees is 1 over tangent. It's positive, so it's just 1. All right, example 5. Evaluate each trig expression at 390 degrees. Okay, let's think about this. where does our angle live? 0, 90, 180, 270. We still didn't get it. 360, and then plus 30 more. So if this is our angle of 390 degrees, right, that would be one full circle and then up to that line. And so remember, we discussed earlier, we can take away or add a full circle and have an equivalent angle. And so what we can do is we can subtract 360 from this angle, and that'll give us 30 degrees. And so 30 degrees is equivalent to 390. And so now we can use our hand trick now that we've got an angle between 0 and 90. Right? So sine of 390 would just be equal to sine of 30. So then we would fold down the index finger, square root of fingers below over 2. Cosine of 390 is equivalent to cosine of 30. Square root of fingers above over 2. Tangent of 390 is equivalent to tangent of 30. It's also equivalent to sine over cosine, or square root of fingers below over above. We get square root of 3. All right, cosecant of 390 is 1 over sine of 390, so 2 over square root of 3. All right, we discussed before, this would be 2 square root of 3 over 3. Secant of 390, 1 over cosine of 390. So 1 over 1/2 turns into 2. Tangent of 390, 1 over cotangent of 390 is 1 over tangent of 390. That's 1 over square root of 3. Multiply that by square root of 3 over 3. Well, square root of 3 over square root of 3, sorry. Anyways, that's what it simplifies to. All right, example 6. Evaluate each trig expression at negative 270 degrees. Okay, what does a negative angle mean? Well, we just defined our rotation this way going positive. All right, and so in that case, then this way would just be negative. Right, so a counterclockwise angle is positive in the math notation, and a clockwise angle would be considered negative. So then where is our, let me make this a little smaller. Oops. So where does our angle live? Negative 270. Well, remember regular 270 is 3/4 of a turn. So we're just going to go 3/4 of a turn the other way. So 1, 2, 3. That's just the positive y-axis, right? So then that means that we also could have an equivalent angle if we add 360 to negative 270. We get positive 90 degrees, right? So that's the equivalent angle. So another way of thinking about this is like if you turn left 3 times, same thing as turning right once. And so to use our hand trick with an angle of 90, we would fold down our thumb. So sine of negative 270 is equal to sine of 90. Oh yeah, by the way, we're in quadrant 1, so we don't have to worry about the signs and stuff. For sine, it's the square root of fingers below over 2, so square root of 4 over 2. That's 2 over 2, that's 1. For cosine of 270, that's equivalent to cosine of 90. All right, square root of fingers above over 2. There are no fingers above your thumb, so it's 0. Tangent of negative 270 is equivalent to tangent of 90. That'd be sine over cosine, or you could say square root of fingers below over above. Either way, you end up with something divided by 0. And so that's going to be undefined, right? And also that makes sense with what you know about the slope, right? If the slope of the line is going straight vertical, then the slope is undefined. And so that's why tangent is undefined, because tangent returns the slope of the line at that angle. So then cosecant of negative 270 would just be equal to 1 over sine of negative 270. 1 over 1 equal to 1. Secant of negative 270 is just 1 over cosine negative 270. 1 over 0 is not defined. And then cotangent of negative 270. I guess if you defined tangent as undefined and then looked at it, you might think, okay, maybe cotangent's also undefined. So you want to be a little careful there. So remember, tangent, using our hand trick, is going to be the square root of fingers below over above. And so it might be better to refer back to the hand trick for cotangent here. We would do the square root of the fingers above over below, right? Just flip that expression. And so with your pinky held down, it would be 0 divided by square root of 4. And so it gives you 0. All right, example 7. Evaluate each trig expression at 1050 degrees. Notice now if we subtract 360, our angle is still not between 0 and 360. So where is it? Well, you can just keep doing that. If you're not sure, you can just, think about it 360 degrees at a time. All right, so we take our angle 1050, we subtract 360, that would be 690. Do that again, and we get 330 degrees. That's between 0 and 360. So that means we have 2 full turns plus 330 degrees. So our line's going to be somewhere over here, right? We're going to have 1 turn, 2 turns, plus 330 degrees. So now in order to use our hand trick, we're going to need to find the reference angle between 0 and 90. That's going to be this one, right? So the difference between 360 and 330, that'd be 30 degrees. So we can use our hand trick using 30 degrees, right? Also remembering that we are in quadrant 4. So cosine associated with x will be positive. Sine associated with the y is negative. The tangent associated with slope is negative. So then for 30 degrees, you would fold down your ring finger. So the sine of 1050 degrees, which is equal to the sine of 330 degrees, which is equal to the negative sine of 30 degrees. We're going to use 30 as our reference, right? Square root of fingers below over 2, that's 1/2. And, like we mentioned, it's negative. Cosine of 1050, that is equivalent to cosine of 330. That's equivalent to cosine of 30. Square root of fingers above over 2. And because we're in quadrant 4, that one will stay positive. Tangent of 1050 is sine over cosine. You could determine it that way. Or using the hand trick also, we've got square root of fingers below over above. Square root of 1/3. Right, that's just 1 over the square root of 3. And we can multiply it like before, square root of 3 over square root of 3 to derationalize the denominator. Cosecant of 1050 equal to 1 over sine of 1050. So 1 over negative 1/2, that's negative 2. Secant of 1050 is equal to 1 over cosine of 1050. So that's 2 square root of 3, right? And if we multiply this times square root of 3 over square root of 3, 2 square root of 3 over 3. Cotangent of 1050 would then be 1 over tangent, right? Let's just do the 1 over square root of 3 over 1. So that'll just be square root of 3 over 1. And we should have multiplied our tangent negative, okay? Make sure you don't forget. That means cotangent will also be negative. Okay, so now let's get into a little more interesting examples. Example 8. Evaluate cosine of negative 8 pi over 3 times cosecant squared of negative 8 pi over 3. Just for the record, cosecant squared is equivalent to the cosine of the angle squared. So the first thing we're always going to want to do when we see these reciprocal functions is we want to convert them into sines and cosines. We can express everything, even tangent, in terms of sines and cosines. So anytime we do a problem like this, we're just going to convert everything into some form of sine and cosine and see what happens first. So what we have is we have cosine of negative 8 pi over 3 times cosecant is the reciprocal of sine. So it's like saying 1 over sine of negative 8 pi over 3, and then that is squared. Okay, now what about this angle, negative 8 pi over 3? Well, remember we can add any integer multiple of a full circle, and it's an equivalent angle. So the first thing I'm going to do is I'm going to get a positive angle, and then maybe we'll see what quadrant that is in. So negative 8 pi over 3, we're going to add 2 pi. But instead of calling it 2 pi, notice our denominator here is 3. So multiply that times 3 over 3. And that's just saying that 2 is equal to 6/3. And so then that still looks like it's negative, right? We're going to have negative 2 pi over 3. So we'll do it again. Plus another 6 pi over 3. That'll give us 4 pi over 3. Okay, now we know where that one is, right? 4/3 is between 1 and 1/2. So that means it's in quadrant 3. Right, remember a pi is a half of a circle. So 4/3 we're going 1 full pi plus a little bit more. All right, and so that one is not going to really, we're not going to use that one in the hand trick. We're going to use this reference angle here, right? So what would be the angular span? Let's label what we've got. We've got 4 pi over 3. This one is pi. And so this angle right here is just 4 pi over 3 minus pi. And since there's a 3 there, we can call this 3 pi over 3 so that we can subtract it. So then that'll give us 1 pi over 3, right? Pi over 3. We can use our hand trick with that. Remember, in quadrant 3, x is negative, y is negative. So cosine and sine are negative. The slope of the line is positive, so tangent is positive. So the sine of negative 8 pi over 3, that would be equal the negative sine of pi over 3, since sine would be negative. Sine of pi over 3, we're going to fold down our index finger, square root of fingers below over 2. That's square root of 3 over 2, and it's negative. Okay, cosine negative 8 pi over 3. That one is also negative cosine of pi over 3. For cosine, it's the square root of fingers above over 2, which is going to be 1/2, and it's negative. And we don't have to worry about the other ones, right? We convert everything into sines and cosines. So don't worry about tangent. Don't worry about any of the other things. That's it. Now we're just going to use algebra. We're just going to plug it in and go. So let's take this. Wait, how do I copy that? All right, never mind. I draw it again. Uh-oh. All right, so we had cosine of negative 8 pi over 3 over sine squared. All right, now we're just going to plug in the numbers that we got there. So cosine of negative 8 pi over 3, that's negative 1/2, divided by sine of negative 8 pi over 3, negative square root of 3 over 2. That will be squared. Okay. Let's, I guess, just do one thing at a time. So the denominator squared, first of all, it's going to turn into a positive number because it's getting squared. So square root of 3 over 2, that's going to be square root of 3 squared. It's 3 over 2 squared, that's 4. All right. Remember, with dividing fractions, we can just flip them and multiply. So negative 1/2 times 4 over 3. That would be negative 4 over 6. We can also simplify this negative 2/3. Example 9. Sine of 945 degrees times secant of 945 degrees times tangent of 945 degrees times cotangent of 945 degrees divided by cosine of 945 degrees. Okay, now this might look really complicated, but we're just going to do the same thing that we did the last time. And first thing, just convert everything into sines and cosines, and we'll go from there. So we have sine of 945 degrees. Secant, remember that's 1 over cosine. So 1 over cosine 945 degrees. Tangent, that's sine over cosine. And then cotangent, well, actually, we don't even have to worry about that. Tangent and cotangent just straight up cancel each other. But, just to be thorough, we could write cotangent would be equal to cosine over sine. And these do end up just canceling each other out. And then that's divided by cosine. Okay. So now this cosine in the denominator of our numerator is going to move to the denominator. So this thing will simplify as sine 945 degrees over cosine 945 degrees squared. So then now we need to figure out what's going on with that 945 degrees. Okay, well, we'll just subtract 360 at a time until our angle is equal or is usable for us, right? Between 0 and 360, let's figure out what quadrant it's in and all that stuff. So 945 minus 360, that's 585 degrees. Minus another 360, that's 225 degrees. Okay, we can work with that. All right, where is 225 degrees? Which quadrant? We got 180, 270, 225 in quadrant 3. Okay, now remember, we're in quadrant 3. We're only concerned about sine and cosine since we converted everything to sines and cosines. That means that both sine and cosine are going to be negative. Why? Because x and y are negative in quadrant 3. And so we could substitute, for example, 945 degrees with negative sine of our reference angle will be 45 degrees there. And then cosine of 945 degrees, that'll be equal to the negative of cosine of 45 degrees. So now we can substitute in what we had. We had sine over cosine squared. So that'll give us negative sine of 45 degrees over negative cosine of 45 degrees squared, right? And I really prefer writing it this way. as opposed to the little exponent on the cosine, because that's a little misleading. Also, the inverse with the -1, it's a little inconsistent the way that that's used. This is a little more intuitive for me. And also, it helps us to catch that this negative sign is going to go away because we're squaring it. So our end result is going to be a negative number because our numerator is negative. The denominator is going to become positive. So we'll just put one negative because we know the answer is going to be negative. Right? Sine 45, cosine 45. We just use our hand trick. So that's going to be folding down the middle finger. Sine is the square root of fingers below over 2. So square root of 2 over 2 divided by, now whatever we got for cosine is going to have to be squared. Also going to be square root of 2 over 2. And we're going to square that. All right, I guess let's go one thing at a time and simplify the denominator first. Since we're going to square it, remember that negative sign is going to go away. The square root of 2 over 2 is going to turn into 2 over 4. All right, and then now we're dividing fractions. We can just flip them and multiply. So negative square root of 2 over 2 times 4 over 2. 2 times 2 is 4. That will cancel. And so we're just left with negative square root of 2. Okay. So example 10. Evaluate the inverse sign negative square root of 2 over 2. And we're going to put our answer in degrees. Okay. The inverse trig functions is actually really where the hand trick starts to shine, because it's super intuitive with the hand trick. Just remember that we have this where our angle or the angle that when we input into sign, it's going to output something. Square root of something over 2. So we're just going to try to format our number into that format. We'll figure out how many fingers. So for example, right, remember sine of an angle is the square root of the fingers below over 2. And so when we see that we're trying to find the inverse of this square root of 2 over 2, well, that means that we must have 2 fingers below. So then which finger has 2 fingers below it? That would be in degrees, our middle finger, so 45 degrees. Now, one thing about using the hand trick to do the inverse trig is, remember the hand trick, we use the reference angle between 0 and 90. And so what we get as a result of the inverse sign using the hand trick, it's always the reference angle. And we need to figure out what quadrant that we're in. And so we have sine inverse of a negative. So which quadrants are sine negative? The bottom ones, right? So that would be quadrant 3 or quadrant 4. And so remember, we discussed that that the output of inverse sine is only going to be in quadrant 1 or quadrant 4. And so that means then we need to use quadrant 4. So then basically we're saying which angle has a reference angle of 45 degrees in quadrant 4, which is going to be between negative 45 or negative 90 degrees and positive 90 degrees, right? And so that's just a negative 90. So the answer that we get will be negative 45 degrees. Right? What would be the angle in quadrant 3? It'd be this one, right? With a reference angle of 45 degrees in quadrant 3, right? And remember, we said that the sine is going to give you the proportion of a two-dimensional line's distance in that direction. These two lines are symmetrical across the y-axis, so actually they're going to have the same sine value if we were to use 225 or negative 45 degrees. Also remember that we can add any integer multiple of a full circle, and so our official answer is going to be negative 45 degrees plus or minus n times a 360, right? How many other rotations? Example 11. Let's do the inverse cosine of 1/2 and express the answer in radians. All right. So remember, with the hand trick, cosine is going to give us the square root of fingers above over 2. Now this means our above is 1, right? Because square root of 1 is just equal to 1. So then we have 1 finger above, okay, which angle has 1 finger above it in radians? That would be pi over 3. Right, and remember again, with the inverse trig, that's going to give us our reference angle. We still need to kind of, use our brain as well as our hand with the hand trick, figure out which quadrant that we're in so that we can figure out the true angle. So for cosine of 1/2 a positive value, which quadrants is cosine positive? That's going to be in the right ones. So quadrant 1 and quadrant 4. But then, like we discussed earlier, cosine inverse is going to output in the top 2 quadrants, right? From 0 to 180 or from 0 to pi radians. So cosine output is going to be in quadrant 1 or quadrant 2. And so then that means that our answer must be in quadrant 1. And so since our answer is in quadrant 1, that means that our actual angle is the reference angle. It's the same. It's pi over 3, right? But then our official answer, right, we are going to also account for any integer multiples of a full circle. So plus or minus n times 2 pi full circle. All right, now let's do example 12. Evaluate the inverse tangent of square root of 3 over 3. All right, so remember, with the hand trick, the formula for tangent is the square root of fingers below over above, and they're both in the square root. So we might notice, okay, that it doesn't seem to look like it's going to work, right? Square root of 3 over 3, let's see if we can rearrange this. Okay, so square root of 3 over 3. First thing, both the below and above fingers, they need to be under the square root. So if we bring that 3 into the square root, we're going to have to square it so that it's equivalent. So then that gives us square root of 3 over 9. And then that can simplify to the square root of 1/3. Now, below 1, above 3. Do we have a finger with 1 finger below it and 3 fingers above it? Yes, that would be the ring finger. We're going to do degrees. So then the ring finger in degrees, that would give us 30 degrees. And right, remember, every time we're using these trig expressions, we're going to be using the alpha first. And then we also have to, coordinate what quadrant are we in. So remember, we're taking the tangent which has an output that's positive. Right? Tangent is the same as slope. Which quadrants is the line going through them having a positive slope? That's quadrant 1 and the diagonal across quadrant 3. But tan inverse is going to only output the same as sine inverse output in quadrant 4 or quadrant 1. So then that means our angle must be in quadrant 1. And so since it's in quadrant 1, our angle is actually, the reference angle is 30 degrees. Now, hold on 1 second before we do a plus or minus n times 360. Because let's think about what's going on with tangent. Okay, first of all, we have a line going at 30 degrees. Now, notice that line is going to go this way too. It's in quadrant 1 and quadrant 3. The angular span from the two opposite ends of the line is 180 degrees. And so technically, for an inverse tangent, we are going to do plus or minus integer multiples of a half circle, because every half circle is going to give us the same slope value. All right. Example 13. We're going to evaluate the inverse cosecant of 2. And we'll express the answer in radians. So first of all, this one is a little tricky because cosine inverse of 2 does not equal 1 over sine inverse of 2. We have an important thing to remember. If you have an inverse trig function, the argument meaning the thing that's inside, is going to flip. It will be the reciprocal. So what that means is that the cosine or the cosecant inverse of 2 is equal to the sine inverse of 1/2. And it might actually be useful to just prove this first. So one thing we can do then is let's let y equal the cosecant inverse of x. Right, now if we apply the cosecant on both sides, x would then equal cosecant of y. Cosecant of y is just equal to 1 over sine y. Now we can, do a little bit of rearrangement, cross multiplication, and we get that sine y is equal to 1 over x. Now we can try to get y by itself by applying the inverse sine of both sides. And now let's back substitute this expression that we had for y. Cosecant inverse of x is equal to the sine inverse of 1 over x. Okay, so we're trying to figure out cosecant inverse of 2. Yep, cosecant inverse of 2. So that's going to be sine inverse of 1/2. All right. Sine is the square root of fingers below over 2. So using the hand trick, then we must have one finger below. Which finger on our hand has one finger below? It's the ring finger. So that means our reference angle, wait, did I say degrees or radians? Radians. 30 degrees or pi over 6 radians. Now, since we're doing cosecant, which was associated with sine, it has a positive output. So we're going to be in quadrant 1. So then that means our actual angle is the same as the reference angle, pi over 6. And we can have any plus or minus integer multiples of a full circle. Example 14. Evaluate the secant inverse of -1, and we'll express this one in degrees. Okay, now again, like the other one, secant inverse of -1 does not equal 1 over cosine inverse of -1. Instead, it's the same relationship, right? Inverse trig, argument flips. So the secant inverse of -1 would be equal to cosine inverse of 1 over -1. In this case, it's still -1. You could do the same exact proof that we did here, except instead with the secant and cosine. You could do that same exact proof here to prove this. But let's just skip past that part and just evaluate this. Right, so cosine inverse of -1. All right, that does not match the formula that we were looking for. Cosine is supposed to have the square root of fingers above over 2. So then what we need to do is we need to take this -1. We need to try to transform it without changing its value, but transform it to match this format that we're looking for. So first we need it to have a denominator of 2. So we multiply by 2 over 2. -2 over 2. Now we also need the numerator to have a square root. So we're going to pull in the 2 into the square root, so 2 is equal to square root of 4. So now we're really looking at cosine inverse of negative square root of 4 over 2. But when we line it up this way with our hand trick, that means that we must have 4 fingers above. All right, so which finger on our hand has 4 fingers above it? That'd be the pinky, right? And so our reference angle would be the x-axis 0. But which quadrant are we in? Cosine being negative means we got to be on the left side. Right? Cosine negative, that can only be in quadrant 2 or quadrant 3. Cosine inverse output, quadrant 1 or quadrant 2. So that means we're in quadrant 2. So which angle, reference angle of 0 means it's on the x-axis in quadrant 2. We're going to call that one 180 degrees. All right, and then because it's associated with cosine, plus or minus any integer multiple of a full circle. All right. Now let's do the inverse cotangent of the square root of 3 and express the answer in radians. All right. We're not going to run through the proof or anything, but just like the last time, right, remember if it's an inverse trig, I should say inverse reciprocal trig, right? The argument flips. I should have made that a little more clear. It's specifically for the inverse reciprocal. So what that means then is that the cotangent inverse of square root of 3 is equal to the tangent inverse 1 over square root of 3. Does this one match our format that we're looking for? Tangent is supposed to be the square root of fingers below over above. Yes, right? Because square root of 1 is just equal to 1. So that means we got 1 finger below, 3 fingers above. Which finger has 1 below, 3 above? That would be, in radians, pi over 6. Now, which quadrant are we in? Cotangent being positive means that the tangent value is positive. That's going to happen in quadrant 1 or diagonally quadrant 3. Which output quadrants for tangent inverse is going to be quadrant 4 or quadrant 1. So that means that we must be in quadrant 1. So then our angle is pi over 6 plus or minus. Now this is associated with tangent, so any half circle in times pi would be a half circle in radians. Okay, now let's do some real world examples. Okay, so this problem, we have a projectile launched with an initial velocity of 40 meters per second at an angle pi over 3 with respect to the horizontal. Determine the x and the y component of the initial velocity. First of all, draw a picture. So angle of pi over 3 with respect to the horizontal. Draw a horizontal line with respect to that angle of pi over 3. Might be a little more steep. Okay, angle pi over 3. This vector, this arrow, represents our initial velocity, which has a value of 40 meters per second. Okay, now remember we said that we can use sine and cosine to determine the proportion of something that's two-dimensional in either the x or the y direction alone. So this is going to be really useful for us in physics because we can separate out y and x. We can solve for all of those separately. So that's a really common adaptation. We use this in physics. But basically, we can have an x component which is going the same horizontal distance, but just straight in the x line. And likewise, we can have a y component which is the same height as this other vector, but purely in the y direction. And the cool thing about vectors is it doesn't exactly matter where they start. It's more about the direction and the length, the magnitude. And so it's no problem at all to just drag that over. And we form a right angle, right, because y and x axes are always perpendicular to each other. So now we have this right triangle. With an angle of pi over 3. And a hypotenuse, let's just keep everything in meters per second. Then our hypotenuse has a length of 40. Right? And let's just call this one, we'll just simplify it, Vx and Vy. Okay. Now, remember, in physics, you don't always want to just remember x with cosine, y with sine, because sometimes they could also give you this angle. And so what you always need to make sure that you do is start with the SOH CAH TOA relationships in a physics course. Right? And so if this is our angle pi over 3, then our x1 is the adjacent, the y1 is the opposite, and the 40 is the hypotenuse. Okay. Also, this is a right triangle, and so we also have the relationship, a squared plus b squared is c squared, using the lengths of this triangle. That would say the x component plus the y component squared is going to equal the true velocity, the hypotenuse squared. Okay, so with the SOH CAH TOA relationships, then the sine of the angle pi over 3 is going to equal the opposite over the hypotenuse. So Vy over 40. That means we can solve for Vy multiplying 40 on both sides. 40 times sine pi over 3. Now, yeah, I know in physics you would have a calculator, but just, for the sake of this video, doing the trigonometry hand trick, we're just going to keep it rolling with the hand trick. So what would be the sine of pi over 3? Well, pi over 3, remember, that's our index finger. Sine is the square root of fingers below over 3, so that would be square root of 3 over 2. Okay, the 40 and the 2 can simplify. I'll rewrite. No, it's okay. So then our Vy would be 20 times the square root of 3. And now this, also remember, this is representing a real measurement, so it would have a unit of meters per second. What about the x component is adjacent, so we can use cosine for that. So cosine of the angle pi over 3 is going to be the adjacent over the hypotenuse, the x component, over 40. Like last time, we can multiply both sides by 40. And the x component, the velocity, is 40 times cosine pi over 3. Pi over 3, index finger, cosine is square root of above over 2. This is 40 times 1/2. So Vx would be 20 meters per second. All right, let me write this one down. All right, example 17. A forester is using a clinometer and a tape measure to determine the height of a tree. They secure the end of the tape measure with a stake at the bottom of the tree. Then they hike slightly upslope to get a better view of the tree. The forester observes the tree top at an upward angle of pi over 3 and the base of the tree at a downward angle of pi over 6. With the tape measure pulled taut between the base of the tree and the forester's eye, the distance is 100 meters. What is the height of the tree? All right, this one, we're definitely going to need a good picture to understand what's going on. So, let's say this is our tree. Then this would be the height that we are looking for. Now, notice the problem states that the forester kind of observes the treetop looking up, the tree bottom looking down. They kind of went uphill a little bit. So they're somewhere in the middle. And now, from their eye to the bottom of the tree, they have a stake. And they have a tape measure pulled taut at 100 meters. Okay, now we're going to measure angles with respect to the horizontal. So this is just our horizontal line from the forester's eye. The top of the tree is observed at an upward angle of pi over 3. And the bottom is at a downward angle of pi over 6. This was not exactly to scale. But what we can do is we can just separate this into two heights using two triangles with these two angles. So let's call this one H1. And this one H2. And also notice that these two sides right here are shared between the two triangles. And so that might come in handy later. They're not, well, that might come in handy later. So then we can use this to find the height that we're looking for, h. That's going to be equal to our h1 plus h2. All right. So let's do this one just one at a time then. We're going to solve the top triangle first. So here we have an angle of pi over 3. We have h1. That's our right angle. Now, do we know anything else? No, we do not. So actually, we can't solve triangle 1 first. Let's draw this other one, this triangle 2. Now this one, we know the hypotenuse of the triangle is 100 meters. We're looking for this h2. This one is our right angle. We know this one is pi over 6. We know a lot more about triangle 2 than triangle 1. So yeah, we can let's call this one x, right? And like we said, x is the same. Okay, so one thing with the h2, we can go ahead and solve for h2 because h2 is our opposite, right? This one is like our hypotenuse, this one's like our adjacent. I'll label it on here too. Opposite, hypotenuse, and adjacent. All right, so using the SOH CAH TOA relationships, if we know the opposite over hypotenuse, that's the O, the H, that's SO. So we're going to say that the sine of pi over 6 is equal to the opposite over the hypotenuse, H2 over 100. All right, so then we can solve for H2 as 100 times the sine of pi over 6. Right? Sine of pi over 6, we fold down our ring finger for pi over 6, and square root of fingers below over 2. So that's 100 times 1/2. So H2 is 50 meters. All right, we'll hold on to that. Seems useful for us. Now, in order to solve anything on triangle 1, we need at least one more side. And that's where that shared side comes in handy. So if we can find the number of x, then now we know more information about triangle 1. So you can pick if you want to use sine or tangent or cosine. Let's see, for x, let's see. I think we could pick which one we use. It doesn't matter because we know both the hypotenuse and the opposite side. Generally speaking, though, you're doing like a math or physics or whatever, like you probably would want to start with the one that was given to you as opposed to the one that you calculated, just on the chance that you made a mistake finding H2. Maybe, I don't know. Actually, if you messed up H2, you get the whole thing wrong. But, different problem. That could be an approach. So let's just use the one that was given to us. That seems a little safer. So then we want to use the relationship with x being our adjacent and the 100 being the hypotenuse. So that's cosine relationship. So cosine of pi over 6 is adjacent over hypotenuse, so x over 100. Okay, so then that side x is going to be 100 times cosine pi over 6. Fold down your ring finger. Pi over 6 for cosine would be square root of fingers above over 2. So 100 times square root of 3 over 2. Right, the 100 and the 2 will simplify, and then we'll have x would be 50 times the square root of 3. So now we can bring that in to our triangle here. right? We know this one now is 50 square root of 3. We want to know h1, and we know the angle of pi over 3. Now, to solve h1, our opposite, using the 50 square root of 3, the adjacent, that means we want to do the TOA. So the tangent of pi over 3 is the opposite over adjacent, h1 over 50 times square root of 3. So then h1 is 50 times square root of 3 times the tangent of pi over 3. For the tangent of pi over 3, we're going to fold. Okay, yeah, now, okay. We were using the ring finger on the other triangle. Now our angle changed. We're using the index finger for pi over 3. So fold down your index finger. Tangent is the square root of fingers below over above. So that would be square root of 3 over 1. Just square root of 3. So then that square root of 3 times square root of 3 turns into a real 3. And then 50 times 3 is 150 meters. So now we know h1 and h2. So then h1, we said, is 150 meters. h2, 50. Oops. So then the actual height that we are looking for, 100 plus 100, 150 plus 50, would be 200 meter tree. All right, last one. Might get a little weird. All right, last one. Example 18. Geologists use sonar ground-penetrating radar to measure angles of fault lines, to predict seismological events, or to prepare new construction sites. Splits in the subterraneous structure reflect a significantly higher portion of the signal than the surrounding compacted rock, identifying what are known as reflective layers. The geologist has traversed the fault in 2 perpendicular paths and used a clinometer to determine the terrain slope of positive 30 in the north-south and negative 30 in the east-west directions. Help the geologist to determine the overall fault slope angle and direction. In the north-south direction, they traversed 20 meters along the surface at an upward terrain angle of 30 degrees, recording an initial fault depth of 10 meters and a final depth of 20 plus 10 square root of 3 meters. Don't worry about that number. We just did it that way so the hand trick will work. In the east-west direction, they traversed a 30 meters along the surface at a downward terrain angle of 30 degrees, with an initial fault depth of 65 meters and a final depth of 5 meters. Okay, it might seem like there's a lot going on here. I guess maybe because there is. But let's start just by splitting it into the north, south, east, west directions and trying to draw a picture as best we can to help us wrap our heads around what the question is actually asking us. So In the north-south direction, they're walking at an upward terrain angle of 30 degrees. And they walk 20 meters in that direction. And the initial fault depth was 10 meters, and the final depth was more. So we're going to draw a line just decreasing. Right, this distance would be 10 meters. That's the initial fault depth. This distance, the final fault depth, is 20 plus 10 square root of 3 meters. Okay, notice this height, we can break it into 3 pieces. Right, so if we have this one triangle here, let's call this height y1. We're really interested about this bottom line, this red. That's our reflective layer. And so we're definitely going to want to know the angle here. And we're also going to want to know the height and the relation. Let's use capital Y so it's different. All right, remember, like on the tree example, this side here is shared with this side here. So that might help us, might come in handy. Okay, in the east-west direction, they went 30 meters at a downward angle of 30 degrees. So they're going downward and 30 meters in that direction. Now, the initial fault depth was measured at 65 and final depth at 5. So it looks like it should be going up. That height is 65 meters. And then the final depth of 5 meters. Now, just like the other side, we can just break this into, 2 right triangles plus a rectangle. This one, the angle is also 30 degrees, just in the other direction. Let's call this one Y2. And then, like the other side, we're really interested in this reflective layer more than anything else. And so we're going to want to know that. We're definitely going to want to know the angle. And like last time, that shared side, it might come in handy. All right. So one thing we can see from looking at the longer side of these shapes is that the total height can be defined by adding the other 3 pieces that we split, right? So 20 plus 10 square root of 3, the total height, is going to equal our little y1 plus capital Y1 plus 10 meters. Yeah, we could rewrite this as 10, just subtracting off that 10. And then on the right side, 65 would be the total height. That's going to equal our little y2 plus big y2 plus that 5 height of the rectangle. We could go ahead and subtract the 5 off. So 60 is little y2 plus big y2. Okay. We might use those in a second. Okay. So as we see, we can break this into right triangles and rectangles and kind of try to solve it that way. So now just kind of one triangle at a time, seeing, what information can we determine, right? And so I guess if I'm looking at like what's the big picture, if I'm looking at the north-south direction, is I really want to know the angle, and I want to know this distance here. And so in order to do that, we just need to understand what's going on with this bottom triangle. And we're really, if you're a geologist, you only know what you're experiencing on the ground. You're trying to figure out what's going on beneath you. And so we're going to have to use this top triangles to try to figure out what's going on the bottom. And so first we're going to connect them with the height. And then once we know the height, then we'll be able to determine the hypotenuse and the angle, which is really what we're interested in to answer this question. So we don't really know enough with those bottom triangles to start off solving anything with them. But we do have quite a bit of information with the top triangles. So this y1 right here is my opposite of my angle. The 20 is my hypotenuse. So that means I can use sine of 30 equals opposite over hypotenuse equals y1 over 20 meters. So that means then y1 is 20 meters times the sine of 30. Sine of 30, we are going to fold down the ring finger, square root of fingers below over 2. So that would be 20 times 1/2 meters. So y1 is 10 meters. Okay. Now we can solve for the big y1, because the big y1 is going to be 10 plus 10 square root of 3 minus y1. Right, and so then the 10 minus 10, that'll give us just 10 square root of 3 as the length of our y1 side. All right. Now, if I'm looking at this bottom triangle, now we know one side. We don't really know anything else. We need something. And so that's where that shared side comes in. We need to find what's the length of this adjacent side. So it's adjacent, we have hypotenuse, we can use cosine. So cosine of 30 degrees would be the adjacent over the hypotenuse. I guess let's call this one x1, just to give it a name. So it would be x1 over 20. So then x1 is 20 meters times cosine 30. Cosine 30, we're going to fold down the ring finger. Square root above over 2 is square root of 3 over 2. All right, the 20 and the 2, a little bit of canceling, and we get 10 times the square root of 3 meters. So now we have enough information about this triangle that we can start using it. All right, this y1, we said it's 10 square root of 3. And this x1 from the blue triangle is the same as this horizontal of the red triangle, is also 10 square root of 3. And so you might just notice right off the bat that that they're the same, and so the angle must be 45 degrees. But if not, right, you can still use the SOH CAH TOA relationships to solve this. And so what we have is our opposite and our adjacent. So we want to use tangent is equal to opposite over adjacent, which is just 10 square root of 3 over 10 square root of 3. right? Which is just 1. And so what we're going to need to do is we're going to need to figure out, okay, what angle has an inverse, or what is the angle with inverse tangent of 1? Right, and that one is not going to work directly with our hand trick, right? Remember, we need tangent to be the square root of below over above. But when it equals 1, then we can just say that the fingers below equals above, right? And so which finger has the same amount of fingers above and below it is the middle finger on the hand trick. And so that's going to give us 45 degrees. Right, and it's a downward angle. So maybe we should write it as negative 45. Because the direction might matter. Okay, so then that gives us the angle in the north-south direction of negative 45 degrees. We can do a similar process to figure out what's going on in the east-west direction. So using this top triangle, we can solve for that y2, and then also we can call this one x2, right? It'll be the same process, solving for the height, solving for the other side, so that we can end up knowing the angle. The angle is going to be what we're ultimately most interested in. All right, and so from this one, the y2 is my opposite, 30 is hypotenuse, so I can use sine of 30 equals opposite over hypotenuse equals y2 over 30 meters. That means then that y2 is equal to 30 meters times sine of 30 degrees. For sine of 30, fold down your ring finger, square root of below over 2, that's 1/2. So then y2 is 30 times 1/2 is 15 meters. All right, now that we know that, we can solve for our capital Y2 is 60 minus Y2. And we're going to plug in that for our little Y2. So our capital Y2, 60 minus 15, is 45 meters. All right, now we know part of the information. We still want to know that x2, that horizontal side too. So let's do that solving the top triangle. That's our adjacent side. So let's use cosine. Cosine of 30 degrees is going to equal the adjacent over the hypotenuse, x2 over 30. So then x2 is 30 meters times cosine of 30 degrees. For 30 degrees, fold down your ring finger. Cosine is square root above over 2. So 30 meters times square root of 3 over 2. All right, that'll simplify as 15 square root of 3 meters. And now we know that is a shared side on our bottom triangle. So now we know enough about this bottom triangle that we can start to use it. That's our right triangle there. Okay, we have our y2, we have our x2, and we really want to know what's this angle. Our x here, 15 square root of 3. The y would be 45. Since we have opposite and adjacent, then we can solve this using tangent. Tangent is equal to opposite over adjacent, so it'd be equal to 45 over 15 square root of 3. All right. That'll simplify. 45 and the 15 can cancel to give us a 3 over square root of 3. Now, we did an example like this before, right? But remember, because tangent is supposed to be square root of below and above, both under the square root, then what we can do is we can bring in the 3 into the square root. 3 would be equal to the square root of 9. And then we can simplify that to give us the square root of 3 over 1. Now it makes sense with the hand trick. And so it's below over above. So which finger has 3 below, 1 above? That'd be the index finger. That would be associated with 60 degrees. The other one in the north-south direction, we called it a negative angle because as we were traversing, it was going down in height. So this one, I guess it maybe would make more sense if we did it like this. Because the fault is increasing in height as we traverse, it should be measured as a positive angle in the east-west direction. Okay. So now we basically, you can think of the reflective layer as like a plane that's kind of tilted underneath the ground. And it's not, tilted perfectly in one direction or the other. It has like a multi-dimensional tilt on it. And so basically, if we're walking straight in the north-south direction, it appears that this fault is decreasing at an angle of 45 degrees. But if we're walking in the east-west direction, then it appears like this fault is increasing at an angle of 60 degrees. And so how do we determine what's the true the aspect or the orientation? Which way is the fault line actually facing, right? It's going to be somewhere in the middle. And so we can do this by representing the slope of the reflective layer as a vector with components of the east-west and north-south direction. And I'm putting east-west first because we think of that like XY. And I'm putting north-south next because we think about that like Y. Yeah. So east-west is kind of like west, right? North-south is kind of like Y. If you're looking down on a map. And so this video is not really about vectors, but if you wanted to know the magnitude of a vector when you know its components, that's also trigonometry. It's the Pythagorean theorem. So, okay, I'm going to draw the arrow in the direction that you would be walking, perfectly uphill if you were walking on the fault surface. So basically, what direction is the fault going perfectly uphill? So we know as we go east to west, well, let's say we're walking in the east direction and north direction to make that really clear. So as we walk east, it is increasing. So our arrow should be going somewhere to the right. But as we walk north, it's decreasing. That means as we walk south, it's increasing. And so then basically that means that our true angle of the where you would be walking up would be somewhere like that, somewhere between south and east. And so if you wanted to determine, what was the actual angle, we can do that kind of in a similar way we used the Pythagorean theorem earlier. Right, but we have an inclination of 60 degrees here, negative 45 here. And so our scalar slope using the Pythagorean theorem would be the square root of 60 squared plus 45 squared. All right, yeah, from this point on, we would need a calculator. The point of the video, is to make the trigonometry hand trick. But yeah, it gets a little weird at the end. We do need a calculator for this part. So square root of 60 squared plus 45 squared, that's going to give us 75. And so what that means is that the if you were on the actual fault surface, it would appear like it has an upward angle of 75 degrees. It's just that when you were walking in the north-south or the east-west direction, you weren't walking perfectly uphill. So you experienced it you weren't experiencing the true slope. You were, not exactly walking fully uphill, kind of off to the side. So that's why we measure different angles on those different directions. But that's how it comes together. So the scalar slope being 75 degrees. And then what about the aspect? The aspect would be the direction, like the cardinal direction in the north-south. And so we can do that by trying to determine this angle here, which again, we have opposite and adjacent. So that's like saying the tangent of the angle of the aspect is opposite over adjacent. So negative 45 over 60. That'll simplify as negative 3 over 4. But honestly, we don't need to simplify it because we're going to use a calculator for this part. The angle, yeah, actually, you know what? Don't even, if you're using the calculator, don't even mess with head stuff. So we're going to do inverse tangent of negative 45 over 60. And that gives me negative 36.9 degrees. And so that would mean then that this angle is 36.9 going down. And so normally with math courses, we're measuring from the horizontal. But then this is where, one of these like physics problems might be a little different because we're going to measure, from the north. If you're using a compass, you want to know how many degrees from north. And so that one is just going to be 90 plus 36.9 degrees. And so then we would get 126.9 degrees. And I guess you would define that as east-southeast. All right, well, that's my video on the trigonometry hand trick, plus a very super in-depth review of what you need to know about trigonometry, as well as a little bit of strange examples towards the end. I hope you enjoyed it and learned something. Please like and subscribe, and tune back in next time.